Okay. So yesterday in our face-to-face meeting, we looked at a situation or we consider a distribution for data that has the binomial distribution. So so we consider a probability distribution for variables that has a variable that has a binomial distribution. And then we said that variables are said to have a binomial distribution when the outcome is either yes or no, alive or death, occurrence of disease or no occurrence of the disease, infection or no infection. So when you record data of this nature, then we said the data has a binomial distribution, and the probability distribution describing a binomial random variable is described as this. And we looked at two examples. The first example was on the probability of one test turning out to be positive out of 5 people tested for COVID-19 diseases. And then we were saying that for COVID-19 disease, and we said that we assume that the probability of having the disease or probability that you test positive for the disease is 0.5, 50-50 chance. And we did the computation here. Then we also discuss this particular problem here, where we look at a situation where pill is cheap or pill is not cheap. So we looked at these two situations, and then we discussed how to address the following issues. Today we are going to move to the next one. Okay, so we also discussed the Poisson distribution, which is here. So we looked at the Poisson distribution, and under this one, we stated that when you are collecting information or data and your interest is just count, let's say for every day in a particular hospital, how many newborn babies did you record? So maybe today, 20 newborn babies, the following day, 15 newborn babies. So you record the number of babies born per day in a hospital. Then what type of distribution will that data have? And then we said the data will have a Poisson distribution. So when the focus is just counting items, then we have a Poisson distribution. Now, what is the rate of birth? Now, let's assume that we are looking at COVID-19 cases every day. How many cases do we record for COVID-19 every day? So that we want to know the rate of COVID-19 occurrence in every day. So that the lambda you have seen here is measuring the rate of occurrence of the disease. So if I'm able to record how many cases we have in every day, then I'll average the cases over maybe 10 days or 20 days or 30 days, and then I'll get my lambda. So once I put my lambda here, then I'll be able to then know what is the probability of 2 cases, 3 cases by just changing the values of X. And that was what we did yesterday with an example here. Oh, yeah. So here we looked at this example. I don't know why this thing is. So yesterday, this was the example we looked at, where we assumed that the maternity ward of Sunyani Municipal Hospital has 60 beds in terms of capacity. And on average, there is 12 breakdown per 5 working week. So if we want to get the average breakdown in a day, that is going to be 12 divided by 5. And that means our lambda is going to be equals to 12 divided by 5, and that is 2.4. And we can substitute that into our Poisson, and then we have this. So today we are going to look at the other distribution, which is called the normal distribution. The normal distribution. I don't know why my computer is moving up and down like that. Yeah, so we are going to look at the normal distribution, which is here, the normal distribution. Ignore the uniform distribution here. We don't really need much here. Let's focus on the normal distribution. So the normal distribution is defined by the mean and the variance. And how do we define the normal distribution? The normal distribution is defined as, so that means you need the value for X, you need the mean value, that is the average of the data set, and then you need the variance of the data. And we've done all this, how to compute the variance. So if I give you values for X, if I give you the data values, which is X, then you should be able to find the mean, which we have done. You should be able to find the variance as well. And the distribution or the density function is defined as 1 over square root of 2 pi sigma squared, that is the variance, exponent minus half X minus the mu, divide that by the standard deviation all squared. This is the definition for the normal distribution. So if you have a data that has a normal distribution, a data that is uniformly distributed around the mean, and that is the symmetric situation. So if you have a data that has a normal distribution, then the data is symmetric. There is no skewness. So data that is not skewed, uniformly distributed around the mean or the median, then that data has a normal distribution. And in short, if we have a variable X and we are saying that that variable X has a normal distribution, this is how we write it in simple terms. We just say X, and then you see the small sign here. It means distributed. X is normally distributed. So this symbol stands for distributed, and the N stands for normally distributed. So we say that, so N stands for normal, and this is the distribution sign. So we say that X is normally distributed with mean, and then variance sigma squared. So we are saying X has this distribution. Now, under the normal distribution, most of the data, so under normal distribution, you are not going to have just counts. You can have maybe 2.5, 20.5. You can have the decimals there, continuous data. We've discussed continuous data. So you can have 2.5, 3.5, 10.5, 20.7, and so forth. You can have decimals, fractions in the data. But in the case of the count, you cannot have fractions because you can't have 2.5 newborn babies. We can't have 3.6 COVID-19 cases. You know, we are counting people. You can't have decimals in them. But under the normal distribution where the data is continuous, then we can have fractions in that. And we're saying that the X is normally distributed with mean, mu, and then variance sigma squared. Now, if we say that a data has a normal distribution, then we have the probability distribution function. Now we want to find out what is the probability that the number is between a particular number is between a particular range, or a particular number is greater than the mean number. So here we consider an example. So you can see this graph. When the data is normally distributed, that is how the graph is like. We've seen all these things in our previous lectures. So let's consider this example to illustrate the work of the normal distribution, or how we use the normal distribution to answer or to address problems. Example, if the number of newborn babies per month in a population of monkeys is normally distributed with mean 251, and then the variance is 3. So you'll be given the number of newborn babies in every month. And then at the end of the day, you add the number of newborn babies and then divide by the total number, and then the total number of days, and then you get the average, just like we've done before. So the mean number of newborn babies is 251. And the standard deviation associated with that data is 3. Now we can go back to our normal distribution formula and substitute these values in there. So we can go back to this formula. We know our mean to be 151. We know our mean to be 251. And we know our standard deviation to be 3. So we can substitute them here. If we substitute them just like we did under Poisson and binomial, we then ask a question: what is the probability that the number of newborn babies is between 251 and 253? What is the probability? What is the probability that the number of newborn babies is between 251 and 253? What is the probability that the number of newborn babies is less than 250? So we will use our probability distribution to solve these two problems. Here we have the first part, the A. We have the A. So here what we are saying is that we are looking for the probability that the number of newborn babies is between 251 and then 253. But remember, this time we are dealing with a continuous distribution. And because we are dealing with continuous distribution, we are not going to sum over the points, but we are going to integrate over the interval. So here we are going to integrate from 251 to 253. I hope you guys can hear me. All right. So we have 1 over. Yes, sir. So we have 1 over 2 pi, and then you remember our sigma is 3 to the power 2, and we have negative 1 over 2, x minus 251, which is our mean, divided by 3, all to the power 2, and we differentiate with respect to x. So we have this to find, but you can see that it's not easy to solve this. So we look for the simplest approach by which we'll be able to address this. So if you are using the normal distribution and you are asked to solve the two problems that we have seen in the previous slide, finding the probability the number of newborn babies is between 251 and 253, and that the number is less than 250. So what we do is we resort to what we call the Z distribution, which I may not take you through the derivation or how they come by this, but let's see how we use the Z distribution. So here, if you apply integration by substitution to what we have here, if you apply integration by substitution, you guys have done algebra in first year, right?
No, sir.
Hey, what do you mean by no, sir? I thought
Yes, sir.
I thought the first year's algebra in, yeah.
Yes.
So why are you saying no, sir?
We didn't.
You know,
Sir, we know that.
you know integration by substitution. First year, I think, yeah, first year. You have the current second years. I taught them integrations under algebra to biology and then algebra to MedLab. So why are you saying no, sir? You mean that they didn't teach you that course or what? All right, so
Sir,
let's move on.
learn this one. That's what she's trying to say.
Come again.
We were not taught this one. That's what she's trying to say. We were taught algebra, but we were not taught what you are talking about, please.
I mean integration by substitution. You didn't do integration by substitution?
No, please.
How?
No, please, we didn't.
Maths, statistics.
Did you do algebra to biology or not?
Yes.
Yes,
So you
please.
didn't do
But
anything, you didn't
it
do
was
calculus.
no, please, no. We didn't do calculus. No.
No calculus.
Okay, so let's move on. So to solve this, you use integration by substitution, and then we'll get a distribution called the Z distribution. And the Z distribution is Z equals to X minus mu divided by the standard deviation. So if I want to find a value, if I now want to find a value, if I want to find the probability that the number of newborn babies is between 251 and then 253, then what I'll simply do is I will come and compute the Z value for the 251, and then I'll also compute the Z value for 253. So in this situation, I'm going to substitute 253 here, then I'll substitute 251 here. Then I will divide that by my standard deviation, which is 3. Then I'll compute Z value also for the 253. And in that, I'm going to have 253 minus 251 divided by my standard deviation, which is 3. So I'm going to get 2 Z values here. So by doing that, this is what I'm going to get. So I'm looking for value. I'm saying that what is the probability that the number of newborn babies is between 251 and 253. So the X is standing for the random variable newborn babies. So what is the probability that the X is between, the number of newborn babies is between 251 and 253? This is what you have here. So I will use this to compute the Z. So here is going to be the Z. So you can see what we just have here is the Z. So you have 251, which is the first value, which is this one, minus the mean. But remember, the mean is also 251. Divide by 3, which is the standard deviation. Then you have your Z, and say the other one, which is the upper one, which is 253 minus 251, divide by 3. So if you take 251 minus 251, we'll get 0. 0 divided by 3 will be 0. So we have this to be equal to 0. So Z is greater than 0, but less than. So we are going to have 253 minus 251 divided by 3. And that is going to give us 0.67. So you can see that Z is greater than 0. So we have 0 here. And then also we have this one to be 0.67. Now, what do we have to do? What we have to do is there is a table, which we call the Z table. We will then,
where is the table?
We will then read the value, these values from that table, which I'm going to share with you now.
Okay. We've seen the table.
No, I've not opened the table yet, please. I'm about to share the table.
9 folders.
I'm about to share the table with you, so you just relax.
Okay.
So you can see, look at this table. Look at the top of this table. Can you see on top of this table? Standard normal distribution.
No, sir.
I'm sharing this one with you. Can you see it?
No, sir.
No, sir. No, sir.
Can you see what I'm sharing here?
Yes, sir. We can see
Foster
now.
cannot see.
Can you see this table?
Yes, sir.
Yes,
What
yes,
is
yes,
it?
we can see
Can
now.
see on top of the table is written standard normal distribution.
Yes.
So we are
Areas
going to
under the
read.
standard normal.
So the value that we are going to read, you know, the other part is 0. So ignore that part. Because it's 0, just ignore that part. Go and read. We are going to read 0.67. You know, the value we are going to read is 0.67. Look in this graph. On the left hand side, can you see the cursor?
Yes, sir.
So on this side, you will see that we have 0.6 here. Can you see this is 0.6? Can you see 0.6 here?
Yes, please.
And then when you
Yes,
go on
we
the
have
other
to see.
side, you will see that there is 0.07 here. So you have 0.07 here, and then here you have 0.6. Trace them. So when you trace them, look at this. When you trace them, you will see that the value at that point is 0.2486. And that is the value that is associated with 0.67. So 0.67 will be the value that the other side is 0. So we don't need to read that side. There are situations where that side is not 0. So that means you read the two values and add them. But the other side is 0. So we don't need to bother ourselves reading that. Now I'm taking you back to the lecture slides.
For
Where can you see the lecture slides? Can you see the lecture slides?
Yes, sir.
All right, so now we read the value 0.67, and that value is 0.2486. So the probability that the number of newborn babies is between 251 and 253 is 25%. So if you are looking for the other one, the probability that the number of newborn babies is less than 250. So you will substitute this one. So you can see this one, we are just finding only one side. We substitute 250 into our Z. We substitute 250 into our formula. So we are going to have 250 minus the mean, which is 251, divided by our standard deviation, which is 3. Then we go and read that from our table again and see what the value is going to be. When you take 250 minus 251, what did you get? 250 minus 251, what do you get?
-1.
Divide by 3 will give you what?
10.
Divide by 3 will give
Minus 1, yes.
Divide by 3 is what?
-1.
Divide by 3 is what?
Wait. So we are coming divide by 3.
Minus 0.33.
So minus 0.33. So you go and read that from the Z table. Okay.
Minus 1 divided by 3 is good.
So you go and read that from the Z table, and that will give you the pro. I'll get you the tables when we meet next week, or when I'm in office tomorrow. I'll have a copy so that you come and pick them. Also, we have books in the lab which have the tables where you can read them from. So you go and read minus 0.33 from the table. And that will give you the probability that the number of newborn babies is less than 250. So this is an example you can try.
Sir, we don't understand. We don't understand.
Yeah, what is it that you don't understand? Hello?
When you went to the table, like what was there was quite different from what you were showing you.
Come again?
I don't know. It seems like when you went back to the table with the 0.7 and then that was 0.6,
Yeah.
when you did the treating, at the end of the day, the value there is quite different from what you had for the final, which is
What value did we get in the table?
I mean, I saw something like 0.1.
No, I'm asking you a simple question. What did we get from the table? When we read the table, what value did we get?
You had 0.2486.
And what did we get? What value are you comparing it to? And you said they are different.
Okay.
0.24.
You are saying that the value we have from the table is different from a particular value. Which value?
No, the way you showed it, like the way I saw it, that's what I'm saying.
Which one?
The same.
If you are not sure of something, just say it. What is it that just be clear so that we'll help you and move on. We don't have time.
No, please,
Different from the.
if you can go back to the table, it will be fine.
No, but what value did we read in the table?
Yeah, in the table, we read this, but what was there, I don't know whether it tallies with what is here. That's what I'm saying. It wasn't too clear, as in when you showed it.
Yeah, you go and if you understand how to find it, you just go and trace and then look for the value. You should have stopped there. You don't let us sharing slides and it's waste of time. Because you waited, we shared the slide, we read something, we moved, then you say you don't understand. If you don't understand, you should stop us there so that we explain to you. Slide. Yeah, can you see the screen? Can you see the screen?
Yes, please, you can see.
So what is it that?
Yes, please.
From what is in the table?
The table hasn't come yet, please.
Okay, you wait, it's coming there.
Okay, thank you.
Yeah, can you see it now?
Yes, please, I can see.
So what is the problem?
Oh, okay, say.
We are reading 0.67 and we've read 0.6 on this side. Then we read 0.7 on the other side. Cross trace them and then you get this value.
7. It's true. Thank you. Please, thank you.
Welcome.
So it was 0. And this is it. This is okay.
Can you see the lecture slide? Can you see the lecture slides? Oh,
Yes,
sorry.
sir. Yes, sir.
Okay, so now let's look at another example. Under example 2, assuming
Yes,
the
please.
mean from your data is 4 and the standard deviation from that data is 8. We want to find the
Yes,
probability
please.
that a normally distributed random variable lies between 2 and 8. So if you have a mean from your data set to be 4, and then the standard deviation is 8, we want to find the probability that a normally distributed random variable x lies between 2 and then 18. Then to do that, we just repeat what we've done in this bullet number 1. So we'll take 2 minus 4 divided by 8, and then we take 18 minus 4 divided by 8. So here we have 2 minus 4 divided by 8, and then we have 18 minus 4 divided by 8. And that is going to give us minus 0.25 and then 1.75. So what we are going to do, we'll go to the table and read 0.25. So we are going to read 0.2 on the other side and 0.05 from the other side. And the value we are going to get is going to be 0.0987. And then we go to the table again. So we'll read 1.7 on the other side, and then we read 0.05 on the other side, and we are going to get 0.45. So let's go to the table. So on the table, we are going to read negative 0.25. Oh, I'm opening the same thing. Where is my, let's see. So in this table, can you see the table? Can you see the table?
No, sir.
Yes, sir. Yes, sir. Yes,
No,
sir.
sir.
Can you see the table now?
No, sir. No, sir.
No, sir.
No,
Can you see it?
yes, sir. Yes, sir.
Okay, so first we are going to read the negative. So just ignore the negative. So we are not, the table takes into that into account. So we are going to read 0. So you know it's negative 0.25. So we are going to read 0.2 on this side. So this is 0.2. And then we look for 0.05 on the other side. And that is 0. So 0.05 is here. Now 0.2, trace that and see what you are going to get. 0.2 up to 0.5. So you can see we are going to get 0.0987. And that is the value for 0.25. Then we read also 1.75. So 1.75. So we read 1.7 here. So you have 1.7 here. Can you see 1.7 here? So we have 1.7 there. And we look for 0.05. So from 1.7, then we look for 0.05. And 0.05 is here. So our value is 0.4599. So we add these values. So we are going to add the value that we had here, which is 0.0987, to where we have the 0. Where is it? The 7. Okay, it's here. So we add that to 0.4599. Let's go back to our lecture slides. This thing is always not showing me. Oh, where's my lecture slides? All right, so we are back to the lecture slides. Can you see the lecture slides?
Yes, sir. Yes, sir. Yes, sir.
All right, so you can see that the probability is 0.987, and then plus this probability, which is 0.4599. We add these values, and then we get 0.5586. So the probability that the random variable lies between 2 and then 18 is 55 or 56%. Any question?
No, sir. No, sir.
So you just have to compute your Z value, read that from the table, then you compute this one also from the table, and then you add them.
That means we are on number 4 now. Hey, quiz.
But the problem is here, isn't it?
Where?
This is the problem that we are solving, isn't it?
Example 3.
We are solving example 3. So all along, where do you think we were? So here is an example. You can, no, this is a different problem. So it's not the problem we are dealing with here. So just leave this one here. It's a different problem. Now let's move on to estimation. So that is it. So you have seen that we looked at 3 types of distributions. We've looked at just one continuous data type. That is the normal distribution. We have looked at the binomial distribution and the Poisson distribution as well. And we have seen how we can write the probability distribution for each of them. So under the binomial distribution, we need to know our probability of success, that is P. And we need to also know the number of observations or the number of points that we are going to consider, or the number of trials that we are going to consider. That is our N. Once we know this, then we can find probability of any number having an infection. Then the Poisson distribution, our rate is the lambda. Once we know the lambda, we can find probability of any information that we are looking for. And then finally, the continuous data, which is the normal distribution. And we've said that the normal distribution is defined by the mean and then the variance. And how do we then compute a probability that a certain value is between 2 values? Or what is the probability that a certain number is greater than a certain number? That is what we have done under the normal distribution also. We are moving on to estimation, and then followed by hypothesis testing or statistical inference. So estimation, so as the name suggests, estimation, we try to estimate. So when you find the mean, you are doing estimation. When you find the variance, you are doing estimation. When you find the standard deviation, that is estimation. You are trying to calculate, you are trying to compute, that is estimation. And we have defined these 2 terms before, parameter and statistic. We have stated, or we have learned in our previous lectures, that parameter is a value or an estimate that you obtain using the population. And a statistic is when you use only the sample. So we want to differentiate the parameters here. If you use the population data, that is, if you gather data on the entire population and you compute the mean, we use the mean to represent that. If you use the population data and you compute the variance, we use the sigma square to represent that. If it is the standard deviation, we use just sigma. If the data is just from a sample, not the population, we use X bar to represent a mean from the sample. We use S square to represent a variance from a sample. And we use S to represent a standard deviation from the sample. So whenever you see mean, it means that you are referring to the population. Whenever you see standard deviation or the sigma square, you are referring to that the variance or the standard deviation is coming from the population. And also when you see X bar, what that is saying is that the mean is coming from a sample. And also when you see S square, it means that the variance is coming from a sample. And then S stands for, when you see S, it means the standard deviation was computed using a sample. So now, if you have series of random variables, if you have series of random variables, x1, x2, x3, up to xn, if you have them, and each of these random variables has a normal distribution as this. So x1 will have a normal distribution like this, x2 will have the same normal distribution, x3 will have the same normal distribution. So if we assume that x1, x2, all of them have the same mean, then we are going to have mean 1 plus mean 2 up to mean n. And that is going to be n mean, because you are summing the means from, so this one will have its mean 1, x2 will have mean 2, up to the final xn, which is going to be mean n. So the means, we are assuming that they are the same. So that means we are just going to have n times the mean. And this is a point estimate. It's just a value. And then the variances, each x has its variance. And we are saying that the variance of x1 is equal to the variance of x2 and so forth. So the summation of the variances, we are going to have variance 1 plus variance 2 up to variance n. And that is going to give us n of the variance. And that is also a point estimate. It's because it's just going to be a value. So what that means is that if we want to sum all the x's, that means we are just going to have summation of the x's. And we are saying that xi, just like we've seen under descriptive statistics when we are computing the mean. So if we sum all the x's, x1 up to xn, then that is going to be distributed as the mean that we have here, which is this one, n mu. And then we have the variance to be n variance, which is this one. Then we have it here. We're assuming that the variance and the mean are equal. So this is how this one will be like. Now, we are talking about the mean. If we divide summation of xi divided by n, what do we get? Summation of xi divided by n, what do we get? We get the mean, isn't it? Hello? If I sum the x's and divide by n, what am I going to get? I'm going to get x bar, and then I'll divide this one also by n, so n will cancel n. Then here, because of the variance, I'm going to have n divided by n squared. So that is going to give me n divided by v sigma squared divided by n. So what that means is that I'm going to end up with something like this. So my mean is going to be equals to so x is the mean, is going to be distributed as mean, and then your variance is going to be sigma squared over n. So what that means is that if I'm looking for a mean of the random variable, if I'm looking for the mean of the random variable, then I'm going to have the mean of each random variable distributed as normal with mean mu, and then variance is going to be sigma over square root of n. Is that the same thing as writing it as sigma square over n? Is the same thing. Sigma square over n is the same thing as sigma square over n is the same thing as sigma over root of n. So still under point estimation, here we have a data set and we want to encourage people to exercise. So we want to see the walking distance. What is the average time people spend in walking? So here we wish to estimate the population mean of traveling times between home and university. Some of you travel from home to the university by walking, and we have to assume the population variance, which is sigma square, is known. Let's assume we know the population variance, so that the standard deviation is also known. And we say that let the standard deviation of the data of the population to be 1.4. That is the standard deviation. And we are saying that on a sample of 40, on a sample of 40 days, we use a top watch to measure our traveling time with the following results. So maybe 40 days, you are walking to campus. So the first day, you use 17.2 minutes. The next day, 18.3 minutes. The next day, 16.8 minutes, and so forth. Now, we want to tell people what is the average time one will need to spend to get to campus. So what do? We add these values. We have done that before. We add these values and divide by 40. So if we add these values and divide by 40, then we are going to get a value 17.76. So the average walking time, the average time to walk to campus or to your university is 17.76. That is the mean. Now the question is this mean? Can we generalize that on average it will take 17.76 minutes to walk to the university? Can we say that? So we have to then check how confident can we be, can we have in making this particular decision or statement? How confident are we that it will take you 17 minutes or approximately 18 minutes to walk to the university? So we have found the mean estimate, but here is the question: how good is the estimate? How much confidence can we place on this estimate? To answer this question, we need to use the sampling distribution of X. So we need to create a particular range of values. We need to create lower value and upper value using the mean. And based on that range of values, we'll be able to tell with confidence, certain level of confidence, that our mean is falling or our mean is representing the population, and therefore we can generalize by saying that it will take an average of 18 or approximately 18 minutes to walk to the university. And when that happens, then we are dealing with interval estimation. So we are moving from point estimation to interval estimation. So if we are able to create the interval, then we will be able to say that there is this probability that the mean is actually representing the population or not. And remember, I've mentioned several times that when you are conducting a study, you may want to say that, okay, probability of 95. So when you say probability of 95 confidence, so that means you are accurate 95%. You are committing only a 5% error and 95% sure that your result is correct. That is the statement we want to make. So we need to create an interval using the 95%. So we are saying that we are allowing ourselves to commit 5% error. We can use 99% as well, which we will see in our next lectures. So here, because we are dealing with the mean, and we said the mean of each of the random variable is distributed as this. So that means our Z is going to be the mean minus the mean from the population. So the mean of the sample minus the mean of the population. Remember, when we're dealing with the values, we will say that the value, which is the x minus the mean, but this time we are using the mean of the sample. We are not using value again. We are using the mean of the sample minus the mean of the population, divided by the standard deviation. Now the standard deviation is no longer just sigma, but it is now sigma divided by square root of n. So we have to find 95% confidence interval for the mean traveling time. So for the 95% confidence interval, we will have to then create that. So from our table, from the table, if we read 95% confidence interval, which we will do when we meet, because our time is almost up, we will read these values from the table and then see how we construct the confidence interval for 95. So our time is up. I won't be able to say much here before the time exceeds where we are supposed to stop. So I'm going to end the lecture here. So in our next face-to-face meeting, this is where we are going to continue. Any question? Any question?
No, sir.
Okay, so we end the lecture here. I will share the slides with you as usual.
Please, tutorials.
Thank you, sir.